So it is my pleasure. It is my pleasure to introduce now Pierre Catoire, who is actually a student in my university, University Littoral Côte d'Opal. He will sustain his PhD in a few weeks, by the way, and I'll let him the word now.
Okay, thank you for the introduction. So I'm really glad to speak here at this seminar. I just, yeah, I should share my slides, otherwise it won't work. Okay. Here it is. Okay. So this should be okay now. Does anybody
Yes.
see my screen? Okay.
Yes, we can see your slides.
Okay, perfect. So, yeah, it is a pleasure for me to talk here at the seminar of a non-associative algebra. And so I will go on and just introduce you what I'm talking about. I'm talking about tridendriform algebras and the relations with the Schroeder trees and there is some Opal algebras structure hidden behind. So first, I will say, well, why are we talking about tridendriform algebras? It's just because this structure appears in many applications in mathematics, like pre-probability, Rotter-Baxter algebras, or this kind of thing. So that's why we are quite interested to study this topic. But now I want to introduce you this kind of algebras in detail. So, yeah, so if there is any question, please do interrupt me. I will be glad to answer to any question. So let's go on. So I'll just try to introduce you the definition of what is a dendriform or tridendriform algebra. So it is working. So just I will give you an example of words. So what is a word first? But you just choose a set X, and you define the set of finite words of X denoted X star. And this is just the set of all the finite words you can make with letters of a set X. Just it. And you can see the T of X just the formal linear combinations of finite words of X star. So for instance, if you take X, the set with two elements, so 0, 1, a word of X star is just something like this. It's just a binary word, a finite binary word. And an element of T of X is just a linear combination of some words. For now, the field we just do not have any say. It's just take any commutative field. It's okay. Don't worry about if it should be of characteristic 0 or something like this. No, we just don't care about this fact now. So yeah, and how do we describe dendriform structure? Okay, so let's get to words. There is some operations I can do with words. It's just here I can concatenate them, but I can also shuffle them. So and shuffle will be this operation denoted like this. So you have a word x1, x2, and you want to shuffle it with x3, x4. And what is going on? You just say, okay, I just shuffle the letter x1 in this word, and I shuffle the letter x2 and the other word on the left word, such that the letters of the first word are not getting exchanged. So for instance, there, the x1 is always before x2 and doesn't overlap it. So now just look at the example. For instance, you have this term, and just you shuffle, you do insertions of letters of these words of this word on the left word on the right one, such that the first letter of the left word is always before the second letter of this first word. So for instance, like this. So here you see that the red letters are always ordered. So the x1 always appears before the x2, etc., etc. That's it. So just a way of multiplying words. Okay, and this shuffle product is just driven by something called shuffles. So what is it? I just introduce it to you. So you just take two integers mn, and you say what is a shuffle of type n? It's just an element of this symmetric group of plus n integers, such that it's increasing on the first m integers and then increasing on the n lasts. And this should be a shuffle. So, for instance, a shuffle of type 1, there is nothing more than the identity and the transposition. If you look a shuffle of type 1, 2, just I have, so here, if I draw a line there, I don't know, no, I can't. Here, is always increasing on the two last integers and increasing on the first one, etc., etc. So here, for example, to 2, if I cut my shuffle there, also this way. So, shuffle, but quite natural. Okay. And what Schroeder showed is that the product I've just introduced you when you just insert the letters of this word inside this one without preserving the order of the letters of the left word, is just driven by an action of shuffles. It's just the you sum over all the shuffles and you make this operation. So this is the same operation I've introduced you on the first slides. Okay, so this is just this thing. This is exactly the same thing. And something we need to notice there is that we can break our shuffle product in two parts. First, we can cut it with a left and a right operation. So what does it mean? In fact, if you do x left, so you want first you want your shuffle product to be the sum of left and right, okay? And you say okay, the left term. So if I do x left x prime, it's just gonna be all the words when I shuffle the letters of x with the letter of x prime, such that the first letter of a word comes from the letter of x. It is the same thing. But it is not the same thing. It is just a definition, and this is the opposite. So the first letter, this is all the words when I shuffle those two words, where the first letter is the first letter of the right word, etc., etc. So hence we have this equality, and that makes something. Okay, and what this is just this examples there. So you see there is always two categories of terms. The first one where it begins with x1 and the other one where it begins with x3, etc., etc. That's it. So in here we want to say, okay, what can I do? Can I do an abstraction to find the for this algebra? So what is the natural operation satisfied by this shuffling of words? Okay, so we'll just have three relations there. For example, if you have two ways of shuffling three words. Either you shuffle the two first ones and then you shuffle with the third, or either you shuffle the second and the third word, and then you just and then you just shuffle with the first word. So this is two ways to shuffle words, and there is some compatibilities that should be satisfied. So for instance, this one, yeah. If I shuffle x and y, and I begin with and I shuffle with another word z, and the first letter should be the first letter of this thing, of the words there. It is just the same thing as if you shuffle y and z whatever you want, however you want, sorry. And then you just shuffle with the word X, but beginning with the first letter of X. Just the same thing. If you trace back the position of the first letter, it fits. And there is some other natural operations satisfied there. So first one, second, and third. And that makes you some natural relations satisfied by this. So yeah, and the product is just the sum of left and right. So just for notation. So you can replace it by the shuffle symbol we've seen. Okay, and the abstraction is just to say, okay, what is dendriform algebra? You take a vector space V and two operations left and right that satisfy those relations. And this is dendriform algebra, we call this. And this is introduced by Maria Ronco in 1999. Okay, so let's go on. Now we'll add something to our sets. Our sets will be handled with an associative product called dot. So this will enable us to shuffle letters between each other. So we can multiply the letters of a word. So for instance here, so I just put on for it to say it's completed, something like this. I just recover my the previous terms, and I have new terms like this. So you just do insertion. The last time it was just doing insertions of letters, and now two letters can fuse. But still you have your condition that x1 always appear before x2 in this term, for instance. So that and here, for instance, you have some of examples. This shuffle product is driven by an object called quasi-shuffles. And how does it work? So you just take two integers, n and n, and you define what is a quasi-shuffle. So this time we don't have an element of a symmetric group. We just have a map sigma from the set of integers from 1 to n plus n to another set of integers, and just have the increasing compatibility like before, but we do not have the injectivity anymore. So we can take two values can be taken at the same time. So for example, here you have the map sending everybody to 1. It's just increasing here and increasing here. Here, for instance, you just get there and you have another map that fits, etc., etc. So you have many things. Here, for instance, increasing 1, 3 and 2, 3. Okay. And the product can shuffle two letters is just driven by this set of elements of quasi-shuffles. And just say, when two elements have the same value by sigma, I just multiply the letters. So yeah, so I'll say it again. So if two letters have the same are sent on the same point by sigma, I just shuffle them. That's it. And there is a unit word that is the empty word, as always. Full product. A shuffle also satisfies some equalities and compatibilities. We will say later on. Yeah. And this is the first thing I wanted to say about this. So as before, you can split your product in 3 parts this time, not 2. So the philosophy is the same thing like for dendriform. Just say, where does the first letter comes from? Here, it just coming from the first letter. The first letter is just the first letter of the left word. Here, the first letter is just the first letter of the right word. And here is just shuffling the 2 first letters of the word to make another letter that will be in my word. Okay. And doing the sum of left, right, and middle, I'll just get my shuffle product I've just introduced you. So I can shuffle my just the shuffle where I can put two letters together to get an.
Yeah, sorry to interrupt, there is a question.
Yes.
This is how is dot defined?
Dot. The dot you just take
Yes, sorry. Yeah, I think now it is clear. The dot is an arbitrary associative product.
Yeah, you just take an arbitrary associative product. Exactly. Yeah.
Okay.
Take whatever you want as soon as it's associative.
Yes. Thank you.
Yeah, that's it. Okay. Here we are. Yes, and here there is 3 categories of terms, like we see. The blue ones beginning with x1, the red one beginning with x3. Ah no, this is the black one beginning with x3. And the other ones beginning with the x1 letter multiplied with the x3 letter. And just make this thing. Okay. Okay, and now we'll go on the abstraction side. So, like for dendriform case, we just say what is a tridendriform algebra. So you just take a k-vector space with 3 binary products, left, right, and middle, satisfying those compatibilities. And the star product here is just the sum of left, right, and middle. Okay, so what are those strange compatibilities? So the first one, it really looks like the first one I've introduced you in the dendriform case. Okay, it's just the same thing. You just shuffle your words and you see where is going the first letter. And for instance, we'll do another one, this one, for instance. So here, yeah, I want my product to be associative on the last equation. That's it, yeah. So this equation here, what is happening? So there is, again, 3 ways of shuffling 3 words. The first one, okay, I can shuffle the word X with Y, and the first letter begin with the first letter of Y. Then I shuffle with Z, and the first letter of those words should be shuffled with the first letter of Z. So the first letter beginning my word here is just the first letter of Y multiplied with the first letter of Z. So here I just do this, I just my 3 words this way. I just shuffle Y and Z, but the first letter is the first letter of Y multiplied by the first letter of Z. And I shuffle with X beginning with first letter of those words. And it's just the same thing again. So this is natural compatibilities required on those products. If we want to talk about shuffling words of this kind of thing. Okay. So just a link between these two structure. If you have a tridendriform algebra, you can choose either you can add the dot to either the left or the right product, but just make right origo or left origo, and just say this thing is tridendriform algebra if those 2 things are just dendriform algebras. It's just the same thing. Okay, that's it. Here we are. And now we'll say, okay, when we have a new type of algebras, we want to study 3 objects associated to those algebras. So at first we'll say, okay, is this the algebra about other words there? In fact, no, because if you shuffle 2 words, A and B, if you do A left B, so you just shuffle A and B such that the first letter is the first letter of A, it's just the same thing, like exchanging the 2 words and shuffling such that the first letter begins with the first letter of A here on the right word. So this is something we don't want on to have a free tridendriform algebra. Okay, so this is here. No. I will try to introduce you what is the free tridendriform algebra, and I will use Schroeder trees for this. So, for instance, so what is Schroeder tree? So a Schroeder tree is just the following thing. So this is just planar trees where any node of your tree has at least 2 children. So for instance, here you just have something strange. This is the tree of T0. That's just for technical condition. Here you have the first Schroeder tree. This is this one. You have 1 node and 2 children, and so on. So the trees are not binary. So you could have multiple children, but you have still the condition that you need at least 2 children per node. Okay, so you have all those trees, and we are really looking at planar trees. For instance, let's look at those 2. So this shows that we are not looking at non-planar trees. That's it. Okay. And the root is always this node there, lowest one. Okay. So just some notation. This is a grafting operator that I'll denote V like this. If you have a family of K trees, you denote so T1, V, etc. V, Tk, just graft all those trees on a common root. So, for instance, if you have those 2, you graft them on a common root, it makes this new tree. This tree, you graft those 3 trees to the node, it makes this tree, etc., etc. So this is just a notation. Okay. Now my starting point to look at a free tridendriform algebra. This theorem from 2002 of Jean-Louis and Franco. But just okay, if you have the tridendriform algebra of one element generated by one element, you just have an algebra of a set of Schroeder trees we've given. And the generator is this one. And we also say the operations, so the left, right, and middle operations are given explicitly by the formula like this. What is this, those indexes, for instance? So when you want to shuffle a tree with another one, you need to decompose your tree, seeing what is grafting on the root. Oh, sorry, what is grafted on the root there. You do something like this, and then you shuffle most children with the tree you're shuffling with. And you go so on and so on and so on. So this is clearly an induction formula. And to make practical computations, this is not really efficient. Yeah. So for instance, yeah.
Can you explain what is capital Tn in your equation on the previous page? What are these trees?
The Tn?
Yes.
The Tn is just the set of Schroeder trees with n+1 leaves.
Oh, okay.
Yeah, there is a shift in the indices, but it's not really important. It's just for technical conditions there. I need to have some kind of shift like this. Okay? Okay. Yes. So just, for instance, let's shuffle those 2 trees to see if it can be complicated. So here I want to do the star product of 2 trees. So I need to decompose my product first like as left plus middle plus right. Then I should apply the induction formula, and I'll get my trees there. So this is not really complicated. Here, for instance, this is just the previous computations made there. So it should be quite easy. But here, Here it can be also easy. But you see easily that to compute this thing it's before. And this is really not nice because the more leaves the trees have, the more it will be complicated. So it could be really annoying to compute with those trees using those induction formulas. So just here, so for technique conditions, add a unit to the algebra, and this is this strange tree I've introduced you. This is a tree with like this. Okay. And if you don't like trees, you can. There is also a description of this with packed words. So, so how can we describe the products in a nicer way than just using an indication there? Okay. So, sorry, I've anticipated. If so, we've seen previously that but the shuffles were quite important because they were describing the products. I just had to shuffle to sum of all the shuffles to get my new elements. And my question there is, can I do the same thing for trees? And, okay, so let's go. If you can always see it like a left comb. How is it working? Okay, just start from the root and you go on the path going to the rightmost leaf where you have grafted some. This is just the right comb representation of a tree because this is the rightmost leaf here. Okay. Here, I just replace Vuzagli. It's just the forest, so just the concatenations of those trees, of the trees there. So instead of I just have this is two comb representations, two trees. So let's get an example. Those tree has two comb representations, the right one and the left one. How is it working? So I go from the root to the rightmost leaf. What is grafting here? Did this thing. So I'll just put it there. And so that, what does I have? So I just put this tree, but adds nothing to my representation. And so on, if I the other way, it is the same thing. So the forest appears, I would say. Here, I just see, okay, as I'm here at the root, and what is happening, I graphed two things. This is those two little things there. And there is a case that is more complicated, something like this. So here the edge is just to graft those two things. If you graft this thing and this thing, just recover this tree. And here, if you graft a y and do nothing, and here you do nothing, tree again. Okay. It's just the representation as count of a tree. Take two trees, T and F, and I want to multiply them, to shuffle them. So I will consider T as a right comb, as the left comb, and I will number the forest from F1 to Fk and to K plus 1 to Fk plus 1. And now I would say, how can I make a shuffle act on this pair of trees? Okay, so consider quasi-shuffle of type K and L. K is the number forest of T, and L the forest of S. And I say, okay, I put N the maximum of sigma. And what is the recipe is the following. You look at the maximum of sigma and you draw a ladder with N nodes, exactly something on those nodes. If your index is between 1 and k, fi on the left of sigma I, and if between k plus 1 k plus z, just graph fi on the right. I will call it sigma of t and s. So maybe it's not clear, but I will just make an example just after. So here, okay, shuffle of type 2, 3, and ENS. So 3 on the for the right column representation, same here, and just looking at sigma of t and s, I look at maximum of sigma. This is 3. So I draw a ladder with 3 nodes. And then what I do, I just say, okay, what I do with F1, I look at sigma of 1, just 1. So I should graft this one on the node number 1 on the left side of my ladder. Then I look at the value at 2, make the thing. And I look at the value at 3, but now just mind that we are talking about the forest of this tree, so we should not graft it on the left, but on the right now. And you'll go on. And you get a new. And the theorem is the following. If you have the product was described by induction with variable induction, so the sum of left, right, and middle is just the sum of all the actions of the quasi-shuffles on T and S. So this makes a non-inductive recipe to the product of just have to make a comb representation, and then you shuffle it like just explained, and you get your product back. And just make the same thing. Just have to redraw your trees, keep it nicer and have something. Okay. And say, okay, but what can I say about right, left, and middle? For words, it's just looking at where does the first letter come from. But for a tree, it's just looking at what's happening on the first node of my ladder, on the node at the bottom. Either I graph something on the left side here. Either I graph something only on the right side, or on both sides, so on the right and on the left. It makes a way of splitting my product, fulfilling tridendriform relations. Okay. So now we'll make some Hopf algebra coming in. So first, what is bialgebra? So when you have a bialgebra, you just have a product, usually associative, and you have a cooperation. So a product is just having two objects, and from those two objects getting another one. And a coproduct is just doing the reverse thing. You just have one object, and it makes a way of splitting it to get two new objects. So for trees, we are looking at admissible cats and how it is working. Try to say it clearly. Have a tree, and you'll consider a cut of a tree. What it is, you just choose edges in your tree T. And you want those cuts to be admissible. So what does it mean? So for instance, this one I won't say it is admissible, because if I'm cutting this tree, if I cut here and here at the same time, I don't know what is falling first, what is falling in which order. It's not clear. But this thing, I agree, because I can say what is falling on of my tree and how does it behave. So the condition is just saying, if you take a path from your root to one of your leaves, you are just passing through at most one cutting edge, sorry. So that's it. It's just this condition. And like this, you can clearly say what is happening. You have a component containing the root, but we will denote R of C, RC of T, and there is from my tree, and that I will denote G's, and it is ordered from left to right. So we'll see on an example what's going on. So you take this tree here, and you cut like this. So the component containing the root is just looking at looking like a Y there. And then you have two things falling from your tree. From if you read it from left to right, this first thing falling from your tree, and the other one, this is this term. Okay, so now from tree, we can say, if I have a tree, I can make new tree appear from this thing. So the thing is that we can build a coproduct over my algebra of my shuffle product, such that it is defined like this. So just say what is the coproduct of a tree T, just sum over all the admissible cuts of your tree, and you just put the component with the root on the right side, and on the left side you put something, you just shuffle, so the product of all the trees that fell from the tree, from T. Okay, so you put the root on the right side, and you shuffle everything that fell from it. Is it okay? Yeah? Okay. Go on. And this makes coproduct but compatible with your tridendriform structure. How? So this could be quite technical. I explain in details. So for instance, this tree has no cuts because I cannot. Ah yes, I forgot to say. Yeah, if I choose cut an edge, the edge should be internal. That means that, for example, this edge is not internal. It is not linking two nodes of my tree, where the last one, where one of its nodes is not. Ooh, I'll go back. So an internal edge is linking internal trees, and in internal trees, vertices is not a leaf. That's it. So this has no cuts. For instance, this node is internal, this one, and this node is internal. So this edge, so I can cut it. So here, this is the two terms where I have nothing on my tree. And here, term pairing where this internal edge there, etc. And you have other terms, other examples there. Here you just have, this one is interesting there. So you can do, you can just do nothing to your tree. It's okay. That just makes those two terms. Or we should shuffle in these linear combinations of couple of trees. Okay. So sorry for I forgotten to say it was internal vertices. Sorry. Okay. So something we can also do is just cleaning a bit our computation, our structure. I do a coproduct of a tree. I can split my coproduct in two parts, just looking at what's happening with the rightmost leaf of my tree. And here you will see you have two kinds of terms. Either the rightmost leaf of my tree is on the left side of the tensor product, so here. Either it is on the right side. So it makes a way my coproduct into. So here you have delta left, just where is the rightmost leaf of your tree. And here delta right of t, just telling you that it is on this, the rightmost leaf is on this part. Okay. And does it fulfill some nice compatibilities? In fact, yes. It is. So here, just another way of splitting the coproduct I've shown you just before. And it fulfills something called codendriform compatibilities. So for instance, just take one tree, sorry, and try to split it. Either I split my tree here, and the rightmost leaf is on the left side. Then I'll do it again. I split the left term that contains the rightmost leaf again, and I put the rightmost leaf on the left side. So the rightmost leaf is on position 1. And here, just another way of cutting my tree. I just cut it again, and I put the rightmost leaf on the first answer. And then I cut the last one, and that makes two of the elements of my tensor product. And here, we just notice that the rightmost leaf also arrives in position 1. And it is the same, it is more complicated, but with it is working. This kind of compatibilities that it also fulfills. So, okay. So when we split our coproduct like this, we get something dendriform co-algebra. And so this is quite technical. So the structure, I'll call it 3-2 dendriform. Why? Just because I can split my product in 3 parts, so left, right, and middle. And my coproduct, I can split it in 2 parts. So that it fulfills dendriform compatibilities. It's just the thing. And the same thing as being 2 dendriform, where I put the dot in the right place. And the structure we've just detailed on our trees. So with the right, left, and middle product, and we left and right copy, something called the 3-2 dendriform bialgebra. So just an example of ugly relations hiding inside the term 3-2 dendriform algebra. You want something like this, where we use these terms where you put primes. It's just the coproduct. So for people who knows, it is just to try to. So there is things that we usually study in Hopf algebra when we use Hopf algebra. So we have bialgebra of finite dimension is always bialgebra. In infinite dimension, this is not true. So you have to do a trick that is called the graded dual. And how it is working, if you have chance and you can write your algebra as a direct sum of finite dimensional vector space. Yes, if you can write your vector space as a direct sum of finite dimensional vector spaces, you can consider a reduced dual that is called, and say the graded dual is just the depth of the duals. It is smaller, but still in the dual. And the thing is quite interesting because you have bialgebra, when you took the graded dual, now it is also bialgebra. Okay. And there is something also interesting to look at. If you have bialgebra there, you can look at primitives. So primitive element is just an element such that an element x such that this quantity is 0. So if you think about our trees, you have the impression that if you have a tree that cannot be cut, then this term is 0. For instance, this tree, seen that it was just the unit tensor this tree plus the this tree tensor unit. So when I withdraw the those trivial terms, it makes 0, it vanishes. But there is not only those terms. As you can clean a combination of trees, you can have more elements like you can have more elements than this tree. You can have this combination, and this is primitive because this cat is cancelled with the other one. So, and you will say, okay, I know what is primitive now, but why it is useful. Theorem is useful when you are in characteristic 0 and you have a connected co-commutative operator. But your algebra, the enveloping algebra of the Lie algebra of your primitives. So if, in fact, if you know the primitives of your algebra, you have understand a great part of your algebra. So that's why we're quite interested in looking at primitives. Okay, so I don't know what time left I have, something like maybe 10 minutes, maybe. I don't know. I'm estimating.
Yes, 12 minutes, I would say.
Okay. I did not check the time when we begin, but okay. Here, just that we can either study the graded dual or the primitives. So here, I think the audience can vote in the chat to see which one is which one is preferred there. So I'll let you. I don't know if I can see the chat somewhere. I should be able to, but yeah. Okay. Vote if you want graded dual of a primitive. Just put it on the chat. Graded dual or primitives, and the will be done. So graded dual. Primitives. Ah, okay. One each. If there is equality, I'll choose. Okay. Okay. Just wait a bit again, 20 seconds, and then I'll choose if there is no more votes. Okay. So yeah.
Okay, so just choose, I would say.
Sorry?
Just choose what you want.
Yeah. I'll just take the primitives then. Change. So we'll try now to generate all the primitives to understand our algebra. Okay, so you can take back our coproduct where you have the delta right and the delta left. And those two make your coproduct. And you can define thin notions of being primitive. You can have left primitives, that's just canceling the left coproduct. You have right primitive that just cancels the right coproduct. And canceling the whole coproduct, this would be a primitive, a co-associative primitive. And there is another thing that cancels this thing. It's just doing a primitive, left primitive or a right primitive. It also cancels this coproduct. So just to note this thing, so primitive, the codendriform primitives are just included in the co-associative primitives. It's just being stronger, being a codendriform primitive than a co-associative. So here you have an example. So this tree is a left primitive because I cannot cut the edge such that the rightmost leaf will fall on the left side. And you have one we've already seen, and this one is obviously a codendriform primitive because it has no cuts. Okay. Okay. Just to notice, think called the small Schroeder numbers that we will denote it an. And in fact, the small an counts the number of Schroeder trees with n+1 leaves. So for instance, this one is the cardinality of Tn, but we've just introduced at the beginning. And you have another sequence, so big an, that is called large Schroeder numbers. And it is defined like this. It is A2, and then this is just, okay, you just small Schroeder number with 2 steps before, and you multiply it by 2. And the strange thing here that I don't understand is when you put the Schroeder numbers in the table, the small Schroeder numbers are the large ones. Don't know why, but maybe because it's the two, I don't know, but okay, this is a fun fact there. Here, the numbers increasing really fast. This is something like a super Catalan number. So this is really, really fast. So for instance, here at 10, at 11, I think it should be 1 million, something like this. So it's really, really huge. Okay. So of some algebraic compatibility. So it came from the 3-2 dendriform structure. You can compute exactly. So this first line is just saying that an counts the number of Schroeder numbers of Schroeder trees with n+1 leaves. You can count the codendriform primitives of rank n. You found the big Schroeder number, and is just the Schroeder number that follows this one. Okay. So why it is interesting, because you have this time that is quite surprising, and you say, okay, if you start with a co-associative co-associative primitive, and you multiply it with this tree, with y tree, with a dot product of trees, you just get a dendriform primitive for the rank after. Now you may understand the number of co-associative primitives of rank n is exactly the number of codendriform primitives of rank n+1. And this is why it is working. There is a correspondence between this. And this allows you to, if you know every co-associative primitive, you can make codendriform primitives of the following rank. And now to end up, from the primitives of rank n, can I generate the co-associative primitives of the same rank? To do this thing, I can then just iterate those two steps, can compute everything. Okay, so the thing is that the codendriform primitive of rank n+1, you can compute co-associative primitives of the same rank using something called the brace algebras. So this is not the brace algebra from RUMP, it's something else produced in by Mark. I don't know if it. If you're interested, just look at, but it is not the RUMP. You have a structure that allows you to compute these things now. Just iterating the process. Here, from this thing, you can compute the primitive, the codendriform primitive of rank n+2. Then with the brace algebra, you compute the co-associative primitives of rank n+2, and then you go on, etc., and you can compute. So here, I just end my talk. So if you want and bibliographic details, you have an hyperlink to the original article with the bibliography detailed there. And I thank you for your attention. Thank you very much.
So thank you, Pierre, for your talk. Are there any question or comment? No question, no comment? So I have a question for you.
Okay.
For words, you look at the first letter for the dendriform or tridendriform structure.
Yes.
You can also look for the last letter.
Yes. Yeah, you can look at the last letter for the words that make also a dendriform structure. But the tricky thing is that you may for trees.
Yes,
Looking
this
at the
was
first.
my question. Well, can you do it? Can you do something like this for trees because you have also a
trees,
surface and you glue trees together? Yeah,
for trees it doesn't work. If you look at what's happening on the last one, you find it is not tridendriform. This is quite strange, but this is not tridendriform, and that's why for trees it only works with looking at what's happening on. And for words, you have a thing where you can look either at the first letter or at the last letter of your word.
Okay, thank you. There is a question on the chat. Could you say a few words about applications from Yuli Bilik?
Okay. So, the dendriform and tridendriform algebras are used in. So you can find it in Rotor-Baxter algebras. So when you have a Rotor-Baxter algebra, you can always define a tridendriform algebra inside it. So somehow understanding tridendriform algebras helps to understand some things in a Rotor-Baxter algebra. So this is one thing. Another thing is just in free probability. So in free probability, you can use works of Frédéric Patras and Coruche Mifard. who used dendriform, tridendriform structures to deduce relations in free probability. So this is an application of those algebras. And then I don't know if you know about multivariate Riemann zeta functions. In these things, just generalizations of the Riemann zeta function, and it is defined of the words. And the good structure to look at it is shuffling words. And somehow you have the dendriform structure appearing inside, and it should be interesting to know it more in order to understand the Riemann zeta function with multiple variables. And I don't know if there is something else that comes to my mind now. No. No, maybe I'll find something else later, but for now, I have no more ideas.
So thank you for your answer.
Mm.
Are there any more questions or comments? If not, well, thank you again for your talk, Pierre. So thank you very much.